Okay. So today I'm going to present about the paper that name is Repair is Nearly Generation, which is also called RING. That's dealing with multilingual program repair with LLMs. So this was basically published in the year 2023 in AAAI. So for the introduction, like as you have heard that automated program repair used to take the erroneous program as an input, and then it used to train the neural network in order to create the patches to fix the original erroneous program to the correct code. So the previous works were basically based on the symbolic representations, which took a lot of time, and its accuracy was not based. And even previous some of the persons in combine the neural network and the symbolic, like for the lower languages such as the Power FX and Excel. But the automated program repair takes only the neural network, and it used to generate the patches for the erroneous programs in order to provide the correct code. So this paper basically deals with fixing 6 languages using just a single search engine. And this paper leverages the use of the large language model trained on code, which is also referred to as LLMC. That is the codex by OpenAI to perform the multilingual repair. Multilingual repair is to repair multiple languages using just one search engine. So in order to do that, it basically breaks down into 3 steps. The first one is default localization. That is to identify where the program is wrong. And the second one is to transform the code into the correct code using the candidate ranking. This all 3 terms will be discussed in the coming slides. So basically, it just has 3 steps to do. That is to locate where the fault is, and then to transform the codes using the candidate ranking. So the related works of large language models could be like the first. The input is the text input, and then through the language model, it outputs the summary of the text input. Only the important parts of the text input, and the embedded. So the advent of large language models shows promise for code understanding and generation results, and hence we'll be using this in this paper, not this one, but yeah, large language models on code. So they basically provide the manually buggy lines, but in this paper they are not providing manually, and the large language models uses the fixed few shot examples, but in this paper they have used the smart shot learning, which will be discussed in the coming slides. What is this? So the contributions of this paper, that is Ring, could be as follows. It used to repair 6 languages using just a single engine by enabling the flipping of the interaction between each languages. And for doing so, it employs the use of compiler messages, the smart few shot selection, and the ranking of the candidates. And it has been shown that it was able to outperform 3 of the languages. And it also introduces the PowerShell commands as a new application for the last mile repair. So the approach of this paper is as follows. Like as I mentioned before, that it has 3 stages. The first one is the fault localization. So for example, given a buggy JavaScript code, so this is erroneous code, and we have to identify. The first step is to identify where the error is this. In order to do so, we first have to get the compile error message. That's why we'll be using the compile error message, and the next and this smart selection is buggy fix error programs, which is discussed in the later sections, but briefly saying that it's the fixed programs which will be using it to identify whether the given repair could be successful or not. The next step is code transformation. First, the error code is given, and then we are generating the prompt generation. And then from there, we are learning the few shot capabilities for the code transformation through this example selection that is used for forming the prompt. And the third step is to rank the candidates in order to select which is the most appropriate to generate the patches. So in order to rank the candidates, we'll be using the average log probability, which will be coming in later sections. So the brief outline is this, like the first will be generating where the fault is, and then the next is to transform the code using this example selection and the compiler error message, and then we'll be choosing the best suitable code transformation using the candidate ranking, and then the fixed program is being made. Is it clear till now? So, but it's not only just there could be syntax errors, but there could be also the problem of there could also be errors that have been introduced as the language evolves. The following example shows the use of the tuple in Python 2, but it is not supported in the Python 3. And hence, this search engine is also capable of fixing the errors that can be generated as the language evolves. So coming back to the approach, the first one was default localization through the language tooling. So in order to locate where the error is, we have to get the error message, which is given by the corresponding language compiler. And it has been even noted that just even the text of such as the invalid syntax is also helpful in order to get the fixed patch from the example selection, which we have seen in the previous slides. The next is the code transformation through few-shot learning, which is the second step. So we all know that the programs with similar mistakes have almost similar fixes. So using this intuition, we would be selecting examples from a collection of buggy fixed pairs based on the error message similarity, which was generated using the compiler, language-specific compilers. And because LLMs are capable of few-shot learning, hence this will be useful to generate the smart shot learning. And the example bank will be used for the code transformation in order to get the in order to fix the program, because the similar mistakes have the similar fixes. So in order to capture the differences in language tooling, they implement two methods for selecting programs from the example bank. The first one is the error vector selection, which is nothing but it just treats error as vector, and then select the programs from the example bank by minimizing the L2 distance between error vectors. And the second one is the message embedding selection, which uses the error as an embedding using the pre-trained model, such as the code BERT, and then comparing embedding based on the cosine similarity. So as you can see in the example that there is an extra bracket over here, which is an error. So what it does is it's with the error message, the compiler has formed this error message. It finds the invalid syntax, and from the buggy fix error messages, that is the example bank, it searched the similar types of mistakes, and hence it used to fix the program. So the last step is the candidate ranking. So in this paper, they have used the averaging the log probabilities of tokens selected during the decoding process, and then sorting them in descending order in order to get this candidate ranking. And the extent to which less likely tokens can be selected is done by the parameter called the temperature. So it is known that the temperature is used to get the diversity of the tokens. So the higher the temperature, the more will be the diversity. And as you can see here in the first picture, there is no diversity for 0.2, and hence it is preferable that we don't use the lower temperatures such as 0 or close to 0. So is everything clear, or is there any question? Can I move ahead?
Yes, please.
Okay. So this have been the ring has been evaluated on the 6 different languages, that is the Excel, the PowerFX, the Python, and JavaScript, C, and lastly the PowerShell. So just briefly talking about the data sets type. First of all, the Excel. It consisted of 200 Excel repair tasks that has been collected from the Excel help forums, which consisted of syntax errors and some semantics errors and a ground truth repair in order to know whether it's successfully repaired or not. And then for the testing, it uses 73 tasks. So each consists of at least one type error, and it was annotated with ground truth error. So the type of data sets were like, for example, here the sum function is really very right. But for example, if we do not capitalize sum, then it will create an error. So these types of errors were there in the data sets. So for the PowerFX, it was similar to the Excel. So, but it was having syntax errors and some basic semantic errors similar to those Excel's one, and even a successful repair actually matches the ground truth, and it was compared to the repair engine La Mirage. La Mirage is the last mile repair paper using the text to text translations. So as you can see that this type of in the figure, this type of functions is used for the PowerFX. And the next one is the Python. It collected random samples of 200 syntactically invalid Python code snippets from the data set used in VPy. Break it, fix it. And so Break It, Fix It is a transformer-based repair system that iteratively trains a code breaker that learns to generate realistic errors and a code fixer that repairs such errors. So a successful repair is considered when it is being passed by the Python 3 parser and has a Levestian token edit distance less than 5 from the buggy program. So this is the bad code, and using the break it, fix it approach, it was learned to have no errors and it was fixed. So next is the JavaScript. So it consisted of random sample of 200 JavaScript with code snippets from the dataset released with the tfix. Tfix is also the text-to-text translation, and it was having at least one error or warning reported by the popular linter ESLint. And it was shown that providing the arbitrary windows to codecs resulted in the false edit, and hence we have to extract the hold functions, which was referred to as the extended code snippet. And so JavaScript has two types of data types: one which was having the full extended code snippet, and the one without the extended code snippets. And the successful repair exactly matches the ground truth. The next one is the C language. They evaluated the ring on an random sample of 200 C code snippets that was drawn from the dataset released with DFix. Briefly telling, the DFix paper had this input as an erroneous program, and then they used the attention weights. one with the darker red is the one that was considered as the most probable for the errors. And then it used to fix the error using this attention weights, and it creates a syntax-free program. So this was compared to the doctor repair model, and a successful repair was considered when it is being passed by the compiler without any error, and the repair must be less than 5 tokens away from the original buggy program. So lastly, the PowerShell, it extracted code blocks with at least one space from the question and the expected answers, which were taken out from the Stack Overflow. And since there is no existing language-specific engine to compare with, they did not compare with any other search engines. And in this, a repair was successful if it matches the associated answer code block that was collected from the Stack Overflow. So they have even provided the common baseline, which uses the zero shot as a baseline for all the languages. Here, just we have to input the language in the language area, and the result is being outputted. So I'm going towards the result and the analysis part. So the first one is this viability of multilingual repair? So as you can see, for the Excel, they have compared Ring with Lamirage and Codex, and for PowerFX also the same. And for the JavaScript, they have compared one with the original data set and the one with the extended code snippet, which has all the functions where all the function where the errors were made. And then Codex, Python was compared with Break It, Fix It, and Codex, and C was compared with Doctor Repair and Codex, and PowerShell was compared with just Codex because it did not have any specific search engines. So as you can see, that Ring was able to outperform in most of the cases, but there is some surprising figures. That is for the TFIX, the extended code snippet is really very low. Sorry. It's really very low. This could be the reason could be because this the performance degradation can be attributed for the subsequently longer sequences of the extended code snippets compared to the original code snippets, and that's why it is quite low. And if you compare the other with the Ring search engine, but PowerShell was able to compare really very low. This the reason could be the PowerShell commands are really very small, very short, and the errors are short. That's why there is a degradation in the number as compared to other languages. So the next one is to what extent Ring can perform error localization. So as you can see with the following figure, and like they take the top candidates produced by each system and compared the locations which comes under plus or minus k tokens. So these are the baselines, and the baselines were not able to perform good error localization as compared to the Ring. Ring for every for these 4 languages were able to outperform the baseline models in order to search these error locations correctly. The third, this is also dealing with the error localization. So here, they're basically trying to see how much it was able to perform, how many tokens are used good for making the exact match. So here it can be referred that the successful repairs are mostly tend to be associated with shorter buggy programs rather than the longer ones. And this could be seen with these 2 types of languages, that is JavaScript and Python. So the third one is how good is the code transformation. So as you can see that the fixed shots and the smart shots does not have much variations, but if smart shots still outperform the fixed shots by a few fraction. The reason could be because smart shots are able to learn the errors which are not being known just with the language changes, but also with the evolution of the languages. And the fixed shots were not able to, but there is a very slight fractional change only. So this one is how good is the candidate ranking. So like as you can see for languages like Excel and C, the Ring outperforms language specific engines. So there is a clear distribution difference in the there are clear difference in the distribution, but in Power FX, there is a very slight difference between the distribution, whereas in PowerShell there is like the Ring was not able to outperform the specific search engine in ranking the candidates. Lastly is like the probability, the graph between the kernel density and the token average log probabilities. As you can see that the one like for the less popular languages such as the PowerShell or the Excel, the distribution peaks are further left than more popular languages such as the Python, C, and Excel. This this likely reflects the underlying language distribution in codex training data. Like the example banks are collected from the publicly forms or telemetry data, because and this evolution strictly employs a leave one out strategy in order to build an example bank from the benchmark programs. These example banks are the ones which I called as a buggy fix programs used for the example selection during the code transformation. And the example bank sizes used during the evaluation do not represent a performance concern. So the example bank size does not care about the number of examples. And so it previously also I've mentioned the statement that even if the error message is given without the exact location, it can be helpful for the low-code languages such as the PowerFX and the Excel. So we basically split the error messages using the regular expression such as this, which captures the text and the error and just leaves the following abstracted error message. It does not we do not need the exact location for the low code languages such as the PowerFX and the Excel. So for the concluding this paper, so the Ring is a multilingual repair engine powered by Codex, which was able to flip between 6 different languages, and the various prompt that is designed to convey developer-like information to address the 3 stages of automated program repair, that was the fault localization, the code transformation, and the candidate ranking. And as we have seen that Ring can perform well in multiple languages, and it even outperformed 3 languages as compared to the 3 specific engines in some with little engineering effort. Is there any questions?
To explain smart shot?
like in the fixed view shot, it was able to learn only the specific that was given. But for the smart shot, is like it was able to deal with the ones which were not even which was not in the buggy fix examples.
I don't think I understand it very well. What is the difference between technical difference between smart shot and few shot?
Technical difference could be in fixed shots. It like everything was known, the examples were known, but for the smart shots, it is dynamically learning like dynamically learning from the prompt, like and it was not learning from the predefined fixed examples.
교수님, 이게 지금 제가 채팅창에다가 올려드린 논문을 보면 이 논문도 이제 그 코덱스를 사용해서 프로그램 리페어를 하는 그런 논문인데요. 여기에 보면은 이런 식으로 코덱스한테 어떻게 이제 프롬프트를 줘야 오류가 있는 코드를 이제 잘 고칠 수 있는지 이게 제한되어 있는데요. 여기서는 언어마다 그러니까 퓨샷을 위해서 퓨샷 example을 이제 어떤 걸 쓸 건지를 미리 정해놓은 게 있는데 그걸 쓴 게 이제 픽스 샷이고요. 스마트 샷 같은 경우는 지금 현재 버기 프로그램에 대한 에러 메시지랑 가장 비슷한 오류를 내는 코드들을 선정해서 example bank에서 선정해서 퓨샷에 포함시킨 다음에 이제 오류를 수정했을 때 오류 수정 확률을 이제 비교를 한 겁니다.
그러면은 기존에는 프롬프트를 정해놓고 한 거고 지금 하는 거는 비슷한 예제를 찾는다는 얘기인가요? 잘 이해가 안 되는데.
이게 지금 코드 기본적으로는 figure 1, can you go back to figure 1 please, Aditi? 네, 여기를 보시면 저 가운데 있는 저 주황색 파트 저런 이제 프롬프트를 만들어서 코덱스한테 던져주면 이제 코덱스가 이제 오류를 고치는 건데요. 보시면 이제 주황색 파트는 이 언어에서 그러니까 어떤 오류 프로그램이 있을 때 이 코드를 어떻게 고쳐야 되는지에 대한 예시를 여러 개 포함을 시켜 놓은 거거든요. 저게 이제 퓨샷 example이고 밑에 이제 초록색 부분은 현재 지금 고쳐야 되는 자바 코드에 대한 에러 메시지를 이제 첨부를 한 건데요. 근데 저 위에 이제 주황색 파트를 이제 만들 때 이제 기존의 연구 픽스샷 같은 경우는 어떤 언어에 대해서 가장 대표적인 에러를 몇 개 선정해서 그 코드들을 이제 첨부를 해놓는데요. 이 논문에 제안하는 거는 지금 현재 코드에서 컴파일러가 생성한 에러 메시지 저 초록색 부분 있잖아요. 저거랑 비슷한 오류를 이제 발생시킨 코드들을 아까 아디티가 설명했던 example bank에서 선정해 와서 걔네를 저 위쪽 부분, 프롬프트의 위쪽 부분에 이제 포함을 시킨 다음에 코덱스한테 쿼리를 날리면 오류 수정 확률이 조금 더 올라간다는 겁니다. 비슷한 이제 오류 수정 기법을 사용을 하기 때문에.
그게 그러면 핵심 컨트리뷰션인 건가요?
그런 것 같더라고요. 그러니까 제가 이 논문을 커버하면서 제일 놀랐던 게 이 논문은 뭔가 새로운 모델을 학습하거나 제안하거나 하지 않습니다. 그냥 코덱스를 어떻게 사용해야 오류 수정을 잘할 수 있는지 방법론을 제시하고 있거든요. 그 프레임워크를.
그런 것 같아가지고 이게 뭐 했다는 한 게 없는 것 같아가지고 제가 잘 이해가 안 돼서.
그쵸. 예. 새롭게 뭔가 학습하고 뭐 이런 건 없습니다. 근데 코덱스를 사용해서 어떻게 하면 이제 기존의 스테이트 오브 디 아트 API 모델들보다 심지어는 훨씬 더 많은 언어에서 이제 높은 에러 이제 수정 성공률을 보일 수 있다 이런 걸 제안을 한 논문입니다.
그럼 프롬프트를 어쨌든 다이나믹하게 얘네가 제안한 기법에서 선택을 해주는 건가요? 아니면은 사용자가 골라내야 되는 건가요?
저 프롬프트는 그러니까 지금 현재 오류가 있는 코드가 있고 왼쪽에 있는 파트를 보시면은 오류가 있는 코드를 컴파일러에 의해서 실행을 시키면 에러 메시지가 나오는데 그 에러 메시지랑 비슷한 에러 메시지를 발생시켰던 기존 그 예시 그 example bank에서 그런 오류가 있는 코드들을 선정해 온 다음에 이제 이 프롬프트에 포함을 시키는 겁니다. 근데 이거를 고르는 방법이
나와 있나요?
예, 코사인
DB
시뮬러리티를 사용을 합니다.
그 DB에서 그냥 불러오는 거네요. 프롬프트에 쓸만한 것들을.
네네. 여기 논문에 나와 있기로는 저 메시지들을 인베딩을 해가지고 코드 버튼으로 인베딩을 해서 그 인베딩의 코사인 시뮬러리티가 높은 거를 선정해 온다고 되어 있습니다.
얘네들 데이터를 다 공개했나요?
네, 이 데이터들은 다 공개되어 있는 데이터들입니다.
아, 엑셀이랑 파워 FX랑
아,
공개
그거가
파워쉘 이런 데이터 커먼 베이스라인 아니에요?
잠깐만요.
파워쉘이랑
아, 네, 공개되어
엑셀이랑
있다고 나와
파워
있습니다.
FX.
논문에. 예.
예전에 기훈 학생이 발표했던 논문이랑 비슷한 느낌이어가지고 순서대로 뭐 차례대로 뭐 해보자 이렇게 했더니 성능이 좋아진다 뭐 이런 논문을 발표했던 것 같은데
그쵸. 그러니까는 이게
프롬프트만 바꿨더니 그냥 뭐
네, 사실 뭐 힘이 쭉 빠지는 논문이죠. 뭐 별거 할 거 없다. 그냥 뭐 챗 GPT 잘 쓰면 된다 이런 식의 말이니까.
멀티링구얼 그러니까 뭐 다양한 언어에 대해서 적용할 수 있다라고 얘기를 하고 있는데 사실 코덱스가 다양한 언어를 지원하기 때문에 가능한 거 아니에요?
저는 그렇다고 보고 있습니다. 예.
얘네가 한 게 없는 것 같은데.
네, 저희끼리 봤을 때는 뭔가 그러니까 멀티링구얼을 지원하기 위해서 뭔가 테크니컬하게 제안하는 바는 없고 예, 코덱스를 사용해서 기본적으로 하고 있기 때문에 근데 여기서 또 제안하는 것 중에 하나는 그 멀티링구얼에서 좋은 퍼포먼스를 보이기 위해서 저 에러 메시지를 약간의 프리프로세싱을 거친다고 되어 있는데 so, Aditi, can you explain more about this step?
Um,
아까 레귤러 익스프레션 써가지고
the
만드는
pre-process compiler error message.
Yes, yes.
So basically, what they are doing is they are generating this compiler error message in order to get the similar type of fixes from the example selection that is being used for the code transformation.
네, 그 정도인 것 같습니다.
예. 어쨌든 오픈 AI에서 만들어 놓은 코덱스라는 모델을 프롬프트만 조금 바꿨더니 성능이 높아졌다. 이렇게 이해를 하면 됩니다. 너무 좀 요약한 것 같긴 한데.
그렇죠. 예, 사실은 그게 다인 것 같습니다.
근데 달리 생각하면은 챗 GPT에 대해서 똑같이 또 시도를 해볼 수가 있을 것 같아가지고 사실상 실제로 테크니컬하게 뭔가 한다기보다는 챗 GPT의 성능을 높일 수 있는 뭐 프롬프트든 뭐든 이렇게 해볼 수가 있지 않을까.
그런 것 같습니다. 예. 그러니까 이런 모델을 저희가 학습할 수 없기 때문에 뭐 관련된 연구를 할 수 없다. 이렇게 생각을 보통 하고 있는데 그러니까 뒤집어서 생각해 보면 굳이 학습할 필요 없다. 이걸 어떻게 하면 이제 잘 쓸 수 있는지 뭐 엔지니어링 이슈로 생각해 볼 수도 있다는 그런 좀 의미는 있는 것 같습니다.
챗 GPT 기술자를 육성을 해야겠네요.
그러게요. 예.
다른 분들 질문 있으면 질문을 하세요. 얘네들은 라스트 마일 에러만 고려하나요? 좀 복잡한 에러는 고려하지 않고.
Yes, sir. Only the last mile error.
근데 라스트 마일 에러는 사실 컴파일러 메시지 보고 금방 고칠 수 있잖아요.
그렇죠. 네.
에러가 이제 간단한 에러만 고쳤다는 얘기인데 사실 컴파일러 에러 메시지만 보고도 자동으로 고칠 수 있는데 이게 랭귀지 디펜던트하게 그런 기존의 뭐 리페어 시스템들이 설계가 되어 있으니까 다양한 언어에 적용할 수 없다. 근데 뉴럴 네트워크 모델을 잘 쓰면은 다양한 언어에 튜닝하지 않고 그냥 사용할 수 있다. 이거네요. 근데 좀 복잡한 에러에 대해서 시도를 해봐야 될 것 같은데.
네, 그렇긴 한데 이제 좀 여기서 비교분으로 썼던 소타들이 다 사실은 각각 언어에 대해서 했지만 다 탑티어 컨퍼런스에서 나온 거거든요. 뭐 웁슬라니, 뭐 뉴립스니, 뭐 익신이 이런 데 다 나온 논문들인데 그냥 단순하게 이렇게만 해도 사실은 그 논문들 1, 2년 전 논문들인데도 다 성능을 제쳐버린 거거든요. 퍼블릭 벤치마크에서. 그러니까는 예. 별거 없는데 그러니까 너무 성능이 좋으니까
라지 랭귀지 모델이 어마어마하다는 거네요.
그렇게 봐야 될 것 같습니다.